let's continue now with chapter number 4, Introduction to Mass Balance. We're going to do problem number 62 from Rachel's Felder book. We're going to talk about the production of iso-octane, which is here. And yeah, it's formed from isobutane and butylene in an emulsion with concentrated sulfuric acid. So here's the diagram. It's kind of, let's say, complex. You have fresh feed, then you mix it with the isobutane recycle, which comes from this distillation column, and then you mix it with this acid recycle because you're recovering acid, and then it enters to this other mixing point where you're going to recycle the emulsion of this reactor. And once you have the emulsion, the acid, and the isobutane, you feed it to the reactor, you make the reaction, and once again you split it for the emulsion. Then you turn this into the decanter. The decanter is going to take out all the acid, and then you send it to a distillation column where you will get only N-butane and iso-octane. So that's essentially what we're going to see. Please pause the video because once again it's very long problem. Let me actually do it. The fresh feed to the process flow rate is about 60 tons per kilo, ton per hour, and contains 0.25% isobutane, 25% butylene, and 5% N-butane. This N-butane is chemically inert, so it's very important to remember that. The fresh feed combines with the 3 separated recycles, which are the ones I told you: emulsion, acid, and isobutane recycles. Okay, this is what I explained you guys. The acid is recycled, okay, overheat from the column is, okay. The overhead from the column contains only iso-octane and N-butane, and the bottom products are recycled. Essentially only isobutane. Yeah, only isobutane. Perfect. The stream entering contains 200 moles of isobutane per mole of butylene. So here you had 200 moles of isobutane per each mole of butylene, and also 2 kilograms of the acid, 2 kilograms of acid per kilogram of hydrocarbon. The stream obtained by combining the fresh feed and the isobutane recycle contains 5 moles. Okay, this is here. Let's say 5 moles per mole of isobutane. Okay, we're going to do this all slowly, so don't worry if you're not getting the idea. The stream, okay. You wish to determine the molar flow rates of each component of the fresh feed, product stream, the emulsion, the isobutane being recycled, and the recycled streams. So let's do that. They tell you to draw and completely label a flowchart of the process. So let's do it. I'm going to do it by myself. First, I have the inlet, which is N0. I don't know how much N0 is, but I know the mass entering, which is 60,000 kilograms per hour. Then I know it's 25% isobutane, 25% butylene, and the balance is N-butane. Then I'm going to mix it here, mixing unit from a recycle. I'm going to draw later the recycle, but let's call it N3. It's only isobutane. Then they mix in A, okay, and once again they mix the acid here. Here's the acid recycle. Let's call it M4, which is essentially, is 9% water and 91% sulfuric acid. Okay, and once again they turn it, let's call this B, they turn it here into a mixing unit, and here is going to enter the emulsion. Let's call it E because it's an emulsion recycled. And finally, once we mix everything, we can actually send it to the reactor. And once again, this is the emulsion. Oops. This is the emulsion recycle. And then they can continue the flow through the process. Let's say it's the decanter. Here you separate all the acid, and here you take the octane, the N-butane, and the isobutane. So which, let's call this N1, N2, and N3. They go here into the distillation column. And you get your product, which is, let me call it P, which is essentially N1 and N2 free of N3, which is isobutane. So let me go and recycle that isobutane. We don't want to drop that. It's money. So here it goes. So isobutane recycle. Isobutane recycle. This is the acid recycle. And yeah, essentially we're at this, let's call this C. This is the E. And let's call this letter D. Here you have N5, N6, and N7 with a little bit of mass of acid. This is the acid at 91%. What do you will have here? Of course, you will have the inert gas, which is N-butane. You will have isobutane, which will be in excess, probably because you are recycling a lot. So look how it makes sense. If you want to have isobutane, you wouldn't need to distillate it here. So you have isobutane in the reactor outlet. And of course our product going out your reactor, you will have your product. If you wouldn't have your product, well, why would you do all this process? So you have your octane here. And now let's make a focus in letter D, which is the stream D, will be N1, N2, N3, and mass 4. So look how exactly is the same this N1. If you will have done a mass balance in here, you know that N1, which is the amount of octane that goes inside, is the same that going outside. So I'm just going to call this N1. N1 enters, N1 goes out. N2 is the same. So this is N, this is octane, and this is isobutane. M4 is separated here, so I'm just going to call it M4. It's the acid. So just an interesting part here, guys, is that the composition in here and the composition in here is the same. But the numbers, for example, N1 is not the same as N5, N7, N2 is not the same as N5, and N3 is not the same as N6. Even though if you would add them and check the composition, those compositions will be in fact the same values, but not the molar flows, okay? So hopefully you get the idea. We have A, B, C, D, and E flows plus product flow. Let me write some notes that we are mixing. We have these notes about 200 moles and 2 kilograms here, 5 moles. So the idea, please guys, is to understand this. Let me do a small explanation. You have NO gets mixed with isobutane. You have a remix here, or recycle. You will mix it once again with acid because you separate it, and then you're going to mix it another time with the emulsion. The inlet of the reactor, very important, is letter C. The outlet will be this letter. I'm not going to choose it, but then you separate it into E and D. Very important. I told you once again, this is the same composition but different mole flows. Then they send it to the decanter. You're going to separate the acid, and you are left with octane and N-butane and isobutane. So probably you're asking yourself, where is the butylene? because we have it here, and essentially all the butylene is a conversion of 100%, so all the butylene that enters will not go out. And I don't remember what, somewhere here I saw 100% conversion. If you read it, you know where, but let me once again. Okay, well, so yeah, it's here. Essentially all the butylene fed to the reactor is consumed. So what does that mean? That it's all the conversion, it's 100%. So you're going to turn all the butylene here into octane. And once again, guys, this is telling you that this is the limiting reactant and this is the excess reactant. Excess. And it's obvious because you're doing this recycle of isobutane. Probably if you wouldn't have a 100% conversion, you will have to, I don't know, maybe you will have here a mixture, or maybe you have to send these guys another time to a distillation that takes out butylene and you recycle butylene and you will have your final product. But the good thing here is that we are converting all the butylene into octane. So let's start doing the mass balances. Well, let's start with the notes. Just to let you know, E is for emulsion. Letter P is for product line. M4 is for recycle of acid. N3 is for isobutane recycle. And N0 is for fresh feed. And C is for reactor inlet. I think you just need that. Maybe I don't want to explain A, B, and D, but you know what's that. So that's a note. Let me add some extra notes. Note 1. We're going to call N-butane as N, and this guy is inert. Note number 2. We're going to assume conversion of the butylene to be 100%. Note number 3. Many of these notes we already told them, but in the decanter, you separate M4 versus N1, N2, and N3. So that's a perfect separation. Probably it's not going to happen, but they tell you to assume it. The recycle in N3, it's only isobutane. What else do we have? Note 5. This is the important one. 200 moles of isobutylene per each mole of butylene. Isobutane versus butylene. Where? At the reactor inlet, which is letter C. Note number 6. The reactor inlet, which is C, you will have 2 kilograms of acid versus 1 kilogram of hydrocarbon. What does that mean? We're going to see that later, but we're going to essentially turn all the moles of hydrocarbon to kilograms. And finally, but yet not least, you have in a flow, after the recycle, of course, 5 mole of isobutane versus 1 mole of butylene. So let me just finish this. Read them. If you don't know where I got them essentially from here to 100, 2 kilograms. This essentially is 100%. They tell you it's chemically inert. What else do we have here? Well, essentially it's all in the problem statement. So now we can actually start our mass balances. So the first thing I want to do is to turn these 60,000 kilograms to moles. How do I do that? You know that moles equals mass divided by molecular weight. The problem here, guys, is that's a mixture. So we're going to calculate the molecular weight or average molecular weight. How do we do that? Is the addition of all the compositions times their molecular weight. And you will see, guys, let me actually write it, that the molecular weights are very similar. Octane, isobutane, butylene, and butane. This one is 58, this one is 56, this one is 58, and this one is 114. So as you can see, we're going to do this here. Let me go up. And we have only isobutane, butylene, and n-butane, which are these. So please expect here that you're going to have a molecular weight or average molecular weight between 56 and 58. If you have something else, you did something wrong in the math. So let's start. It will be the x of n-butane times molecular weight of n-butane plus x of butylene times molecular weight of butylene plus the x of I times molecular weight of I. So just let me change this. I don't want you to confuse it. This means for every species, and I here means for isobutane. So this is 0.5 times 58 plus 25 here times molecular weight is 56 plus 56, oops, 0.5 0.25 times molecular weight, which is 56. Doing this, you should get a molecular weight or average molecular weight of this mixture to be 57 point, yeah, essentially 57. Yeah, kilograms per kilomole of mixture. So let's go back, and yeah, I told you it's going to be either 56 to 58. So yeah, now we can use this formula. Initial moles are initial mass divided by molecular weight or average molecular weight. This is 60,000 kilograms per hour, and that it's about 50 kilograms per kilomole. So I got, doing this, I got 1043 kilomoles of mixture per hour. So that's my inlet. Good. And as you can see, we can already start solving this. They tell you to molar flow rate of the fresh feed. We have it right now, so we're good for that. We still need to do a lot, but good that we have this. So let's start doing more mass balances. Let me do a mass balance in the overall system. That's always a good idea. So that's essentially n0 equals n1 plus n2. And I have n0, but I don't have n1 nor n2. If I do a mass balance in a substance overall, let's choose n, we can actually get n. So this is xn times no equals n. Let me check what's n2. N2 was 4, oops. It's octane, and yeah, it's here. So n2 is going to be this, and I got this. This is this value here, and so easily I got n2. This is, if you do this operation, you should get something around kilomoles per hour. Good. Just let me kilomoles of n butane. Now what else can we do? Let's do a mass balance for octane. Go a little bit down here. Now you know you have your system, you have no inlets, you have only outlets, and there's a production term here. So inlet minus outlet plus production minus consumption should be equal to the accumulation. So steady state, not consumption, we're only producing, and there's no inlet, so my product term is equal to this. So how do we account for the production? Well, we need to know how many moles we are feeding, or moles of butylene. Where is it? Yeah, butylene. So let me see. I know there's 100% conversion of butylene. So everything that enters in butylene turns out to be O. And what's that? The production. So let me calculate how many moles of butylene we are feeding. This is X of B times N of 0 is the moles of butylene. So moles of butylene. X of B is 25%. Butylene is, now the feed is this amount, so this is going to give me the moles of B. Moles of B turn out to be 260 kilomoles of butylene. And I know these turn out to be, let's go to the equation, for every mole of butylene I get 1 mole of, where is it, octane. This is from this equation. So this is butylene, this is isoctane, no, isobutane, and I'm getting octane here. So I need only one, so 1 to 1, I'm going to produce 260 kilomoles of octane. So that's my production. And my outlet, what's the outlet in conversion, is N1. So my outlet is P equals N1, and I already got P, which is 260 kilomoles of octane. This is my N1. So very easily we just got our product stream. If you see N1 and N2, which is here, fresh feed, no, where is it? The product stream. We got product stream and we got fresh feed. We just need to go for the emulsion and isobutane recycled and acid recycled. So we still got job to do. That's cool. What's next? Once we have this, let's continue to do a mass balance on the let's go for the recycle. So for the recycle of isobutane, we need to do a mass balance. Let's use note 7, which states that there are 5 mole of I for every mole of B at the A flow. So let me calculate the moles of I or isobutane in the fresh feed. That's easy one. Actually is this times N0. Xi is 25%, and 1043 I got 260 kilomoles of isobutylene per hour at the fresh feed. Good, we had that for living now. Let's apply note 7, says 5 mole of isobutylene at A, where each mole of isobutylene in the fresh feed. So I know I got 260 kilomoles of isobutylene in the fresh feed. We just need to multiply these, and I got 303 kilomoles of isobutylene at A. So let me, this is a number we're going to use. So N of I at A equals 1303 kilomoles per hour. So this is also important. I'm going to underline it. Now, what else can we use? Let me use logic. So we got this amount of isobutylene. Since we're not going to add extra isobutane, isobutane, so isobutane, the same amount will be here. And as you can see here, you cannot suppose here. So at least A and B is the same. Let me write that under so I can have it also as a reference. So N of I in B is also the same number, because we are just adding acid, and the acid contains no isobutane, so I can suppose that. Now, I think we can, let's reverse it. Okay, we can continue. Let's do a mass balance in the mixing point, or the first mixing point in or on isobutylene. do I have my inlet equals outlet. There's going to be N0. Let's do a mass balance of I. So what lane is entering here, and you go out here. So this is N0 x1 I. This is N3, and this is isobut lane at the outlet, which is Ni at A. So essentially I got N0 times xi plus N3 equals Ni at A. So I can get this quantity, yes. N3 I don't have it. Actually, that's the value we're going to find out. And this value is this one here. So that's the way I'm going to find my value here. 200 minus 260, and I got this value. Good, we have another flow rate. Actually, this is the recycle of isobutane, sorry. Now, what else can we do? Let's continue with the mass balancings. Let's do a mass balance in flow C. We're going to use now note number 5, which states essentially that there are 200 moles of I per each mole of B, of course, in the inlet of the reactor. So please do not confuse. This time is isobutane for butylene. Last time was isobutane in A and isobutane in feed. So there are different things. Let's do it. So let me tell you, and moles of isobutane in C should be equal to that of 200 times the moles of butane in C. Hopefully you get a little bit that. So this value, where do I get that? Where do I know that? I know that I'm going to, where is it? This flow is, well, actually, where is it? Yeah, I know MB equals this amount, which is essentially this amount. Let me just write it. It's my moles in the inlet of the reactor of isobutane is essentially 200 times that of XB times N0, which, why this? Because this amount here will go here, will not change, and then adding acid will not change, and then it turns here, there's no butane, so actually the same amount of butylene is everywhere, in the inlet, in A, in B, and in C. It will be a lot of problem if we will have, for example, here butane, or here butane, or here butane, but we don't have it, so it's easy to do, and we can use that. And let me use values here. 200 XP is 20%, 25%, and 1043. This number here turns out to be 52,000 kilomoles of isobutane per hour. So that's at the reactor inlet. We want to know that also. So as you can see, we have in A, B, and C. We know where is isobutane A, B, and C, and we know butylene it's the same in A, B, and C. So I'm not going to write that, but just keep in mind we got those data. So let's do now a mass balance in the mixing point number 2 on isobutane, which I know. So I have this mixing point here, and you're okay. So it's essentially, this is N6, this is N of I at A, and this is going to be, where is it? N of I at, let's say, C. This is actually B, sorry. So we are doing this mass balance here. I told you it's mixing point 2, I'm wrong, it's mixing point 3. So let me correct that, mixing point 3. And we have that. So by doing mass balance, you know the equation turns out to be equal inlet equals outlet. So N of I at B plus N6 equals N of I at C. So N of I of B, I have it 1303. N of 6, I don't have it. That's actually what I want to get. And this value here, I already got. So N of 6 turned out to be 50,700 kilomole per hour. Good, we're kilomole isobutane. So as you can see, we're fooling all our values here. What else can we do? Maybe we can still do a mass balance. No, I think we need to jump to the mass balance in the emulsion. So mass balance in the emulsion. Recycle should be, let me know what. Okay, not the emulsion, recycle, and actually it's in flow E, and I'm going to also use flow D. So what up, guys? I told you before when I was doing this that you can relate these amounts with these amounts, but you cannot say they are the same, but the relationships are the same. So for example, let me write you this example. The composition of any value in D will be the same composition that any value in D. So the ratios are constant. Ratio are constant. So for example, if I got, I don't know, moles of N divided by moles of I, this is just a relationship, has maybe no sense, but I just want the mathematical value. In E should be exactly the same as moles of N divided by moles of I in D. So just to let you know, for example, if we got, let's say, we got 50% here and here. You have 2 moles and 2 moles, and you have 50% and 50%, and you got only 1 mole and 1 mole. The compositions are the same, but the mole flows are not the same. You have 1 mole, let's say this is butane and this is isobutane, this is butylene and this is isobutylene. You have different amounts, but you can relate butane divided by I is 1 divided by 1 in here, so you're going to have 1. This ratio applies for this. So if I do the same, I divide butane and I is 2 divided by 2, this is 1. So you can see these are the same, the ratios or the relationships are constant. So that's what I'm doing. And hopefully you understand it, because it's a very, very important concept. And I'm going to use it. So N5 divided by N6 should be the same as N2 divided by N3. What's this? Moles of N in E divided by moles of I in E equals the same amount of moles of N divided by the moles of I in letter D, guys. So what do I have here? I have N2. I think I do have it. N2, where is it, guys? Here, N2, 521. So I got 521. N3, let me check if I have it. I think I have it. N3, yeah, 1042. And N6, I do have it. I just calculated, so it's 50. So let me send that multiplying here. And I will get N5 like this. So doing these ratios, I get 25,300 kilomoles of N divided by H, or hour. This is N5. So good, once again we got this. And I will use the same logic as moles of octane divided by moles of isobutane in D equals as the same ratio moles of octane divided by moles of isobutane in the emulsion. So this is essentially N1 divided by N3 equals N7 divided by N6 I have everything, 1, 3, and 6, so N7 equals N1 divided by N3 by multiplying this, so N7 is N1, how much is that? Let me look out for N1, it's 260, and N3, we use it already, is 1042, and N6, we just got it, it's 5700. So doing this value, I got 12,615 kilomoles of octane per hour. So as you can see, we are recycling a lot of octane, 12,000, compared to the production, which is only 260 kilomoles of octane. So this here, I'm taking out of the system only 260, but in this recycle, I have 12,000 kilomoles. So it's a lot, guys. We're recycling a lot. Maybe the process cannot give us more efficient values. We don't know. That's more about chemistry, kinetics, and plant engineering. We're not going to see that. Let's continue. And what else can we do? Okay, so let's relate to note number 6. They tell you there's 2 kilograms of acid per each kilogram of HC or hydrocarbon at the reactor inlet. So we got a problem, guys. We are working with moles, so we will need to change everything to mass. So first thing I want to do is to get the moles, or the amount of, let's go to C. I want to get all these compositions. The amount of N, the amount of I, the amount of octane, the amount of, what else do I have? IBN, butylene, I still have butylene, I'm going to feed it. Yeah, essentially just that, guys. So mass of B equals, I have the moles I feed, and that's only. And in the recycle, I have nothing. Actually, guys, let me write it for you so you can get it a little bit. So I have the inlet of the reactor. Inlet of reactor is either the flow you recycle plus letter B. So yeah, C equals E and B. C equals E, well, B and E. So let's work on it. We want C, let's calculate the mass of B. In butylene, I'm only feeding in B. I have no recycle, so I'm just going to get B. B is going to be 260 kilomoles of butylene per hour. That's easy one. Now let's do isobutane. I actually have it. It's NB 52,000. Oh, I could either say I'm going to add B and E, which this is equal to C. I got C, so I'm not going to add twice. I got moles in isobutane at the inlet is 52,000. Let me put that. So 52,000 kilomoles of isobutane per hour. Now mass of N-octane going to be N5. Well, not the amount I'm going to feed here plus the amount in the recycle of emulsion. Letter B is N5. No, it's N0 times the mole fraction. And the recycle, which is, let me go up and find out, the recycle is this N5. So let me just find out how much is that. It's 25,000. These are values I already got, so that's cool. I don't need to do any calculations, just find those data. Now, Actually, I'm calculating only moles. We're going to turn them with the mass formula later, guys. So I have nothing in B because of course there's no, but I do have in the recycling emulsion. How much is that? That's N7. And N7 I already calculated is 12,650 kilomole of octane per hour. So good, we have all our moles, but we need the total mass. How do I get total mass? Is mass of B plus mass of I plus mass of N plus mass of O. How do I get this? Is moles times molecular weight of B plus moles of I times molecular weight of I times moles of N molecular weight of N and moles of octane and molecular weight of octane. I have everything to do this, so let's do it. The mass of B would be 260 times 56, which is the molecular weight. I got 14,560 kilograms of butylene per hour. So mass of isobutane is 52,000. This is going to be a huge number times 58. I got 3,016,000 kilograms of I. And so on. I keep doing this. This value is also 1 million. This is a lot. 49761 kilograms of N by hour. And final octane. This is also going to be a huge number because it's a bigger or larger amount of molecular weight. 1,442 kilograms of octane per hour. So nice, we got everything. The logic thing will be to add everything. So let's add this. And I got 5.97 times 10 to the 6 kilograms per hour. So good. Now let's get back to note 6, which tells there are 2 kilograms of acid for every kilogram of hydrocarbons. So therefore, if I have 5.97 times 10 to the 6 kilograms of hydrocarbons, how much I have? I only need to multiply times 2. So it's essentially 1.2 times 10 to the 6 kilograms of acid. So that's my recycle of acid. Oops, actually it's to the 7 power. Nice, we're almost done, guys. Actually, we got everything. Let's just answer what they told us to. Letter A is to get the fresh feed, rate, and composition. I don't know why they ask you the composition. It's easy. It's 25 of butylene, 25 of isobutane, and 50 of N-butane. That's a given data. And the molar flow rate equals to N0, which is 1043 kilomoles per hour. So we got that. Now let's continue. The product line, you want rate and composition. The rate is essentially product is N1 and N2. So if you add this, you will have your rate. So N1 is 260 and N2 is 521. You got 781 kilomole per hour. That's the molar flow rate of P. Good. Compositions is essentially 260 divided by 281 and 521 divided by 781. This is 0.33, 0.67. So this is the composition. Good. What else do we need to do? The emulsion. We need rate and composition. So the total amount of moles, I told you, is N5 plus N6 plus N7 plus moles of acid. How do I get the moles of acid? Moles of acid equals mass of acid divided by molecular weight of acid. How do you get the molecular weight of acid? Let's just assume for this to be 90 kilograms. We're going to see it in the next question, how to calculate this. Kilograms per kilomole. So let's do it. N5 is 25,300 and 50,700. This 12,650. And 1.2 times 10 to the 7 divided by 90. This will get me a value of 220,800 kilomoles. But I don't want, well, this is the rate, this is the emulsion rate. But I want also composition, so it's essentially all this divided by 220,800. So compositions is x of I is n6 divided by nt, x of n is n5 divided by nt, x of O equals n7 divided by nt, and the watt of acid is essentially 1 minus x of I, x of n, x of O. So let me calculate these, and these. I got 0.2029, 12.5, 0.62, and essentially I just need to take out all these. I got here 58.4. Good. We have all the compositions of the emulsion. And finally, but not least, I think we need to do a mass balance in the acid. You will see now how I get this 90. So the acid flow rate was 1.2 times 10 to the 7 kilograms per hour, but this is at 91%. So what does that mean is I have 9% of water and 91% of acid. Molecular weight of water is 18, molecular weight of acid 98. So molecular weight or average molecular weight is the addition of all the components times the molecular weight. So 0.09, the one of water is this one, and the one of acid is this one. This gives me the 90 kilograms I was talking about before. Yeah, essentially, if you wanted to calculate the moles of acid, which we already done, but let's do it once again. It's 1.2 times 10 to the 7 kilograms per hour divided by 90 kilograms per kilomole. So I got 132,158 kilomole of sulfuric acid at 91%. So yeah, essentially guys, that's everything. Let me make a small conclusion on this. The process goes as this. I love it because it's easy, because you are making 100 separations. You know everything of isobutane goes here, you know that all the acid goes here, etc. The only tricky parts are understanding this here and this here and this here. So what else do we have here? Very important to write all the notes. We use every note, yes. This one of inert, well, we didn't actually use it, but it was good to know that it was an inert. And the separation of acid, completely acid, we use it. All these molecular weights, we use it, even the octane one. The recycle rates, yes, we use it. 200 to 1, we use it. 2 kilograms per kilogram, we use it. And essentially we did everything. What else do we have here? Yeah, we calculate the initial moles. That's easy, very easy actually. Mass balancing in overall units, that's my favorite part. always do mass balance in the overall system. Many times you get many good answers. Sometimes you will not get them, so don't be that frustrated, you can continue. Now, mass balancing in the Octane, a little bit of stoichiometry. Now the interesting part to start here using Note 5 to 1, we use it and we calculated the moles. We also use logic here, not only mass balancing. You know that in B and A is the same amount, so why not write it? Then also using the mixing point 1, we calculated another flow, N3, which is the recycle of isobutane. Then using Node 5, we do this mass balance and we get this here. What else do we have here? Mass balance in the mixing unit number 3, we got another flow. And this, guys, is very, very tricky. Actually, this is not that common in mass balance, but it makes sense. Hopefully you understand this part. Once again, I'm going to explain it to you. So for example, you got, let's say you have this. You have 3 moles of A and you have 3 moles of B. So you know, of course, that this applies. This is the composition. What happens if I separate 2 moles of A here and 2 moles of B here? Composition is exactly the same. And of course, this will be 1 mole of A and 1 mole of B. Composition is once again the same. It's like splitting a substance. So what happens when I do relationship in, let's say, in this part? I say amount of A divided by amount of B will be 1 mole divided by 1 mole, which is 1. What happens if I do the same here? 2 moles divided by 2 is 1. And the same here, 3. So even though we cannot say that 2 divided by 2 equals 3, we can say this. You cannot say that this and this is the same, and this is the same. Of course, 2 is not the same as 3. But the division 2 divided by 2 and 3 divided by 3 is true. So this is what we did essentially here. It's more about mathematics and mass balance, not that much, but it makes sense. I use it because the problem here is that I got mass flows. As you can see, I got a mass flow here. I didn't want to change it to molar flow. And even though I will change it, I will have to look for it, look for the value, and that's very, very difficult, guys. So yeah, once again, here it is, how I got them. I used this technique twice to get N5 and N7. Finally, this one is also nice. I need to relate everything to mass. So change all the moles using not mass balances, using molecular weights. I got the masses and the total amount. This is mass. Total mass, I got the total mass. And since I'm using 2 kilograms per each kilogram, I just need to multiply twice. And I got my recycle rate. Good. Now since I got everything to do my answers, I'm going to start it. They tell you to calculate the rate. It's the first thing we got, and the composition is actually given, so you don't need to calculate it. Letter B is calculate the product, which is N1 and N2. I got N1 and N2 almost since the beginning, so I got this easily. And finally, well, not finally, the emulsion is kind of tricky. It's the most difficult part. You need to add all the moles. Very important to know how to do this, because you have mass of acid, you need to change it to moles. I got the total amount of moles, and I have my compositions here. And finally, we do the acid flow. We change everything to moles. Of course, the composition is also given. 91% is water, and 9% is water, and this is acid. And we're done, guys. I think this is a very good example of a mass balance. You practice a lot, multiple units, recycle, purge, stoichiometry, and yeah, essentially we're done. See you in the next problem.